This is the lecture on the sampling distribution of the mean. This goes along with the previous lecture, sampling distribution of the proportion. This will be almost perfectly analogous to it. We'll cover the same material, except where before we had a categorical variable, now we will have a numerical variable and look at its mean. So, for example, we could consider the numerical variable a young man's height. That's a bell-shaped variable with a mean of 70 inches and a standard deviation of 2.5 inches. What does that mean? That means a randomly selected man on average will be 5'10", but any value between 5'5" and 6'3", that is within 2 standard deviations of the mean, would not be unusual. That gives you a sense of what you would get if you did that probability experiment. Now I want to change the probability experiment. Suppose I take a sample of 12 men, I measure all their heights, and average them to get the sample mean x bar. What kind of numbers would I expect to get when I do that? On average, I think it's pretty reasonable. I would expect to get 70 inches. But each sample might give you an x bar a little higher or a little lower than that. How much? What values would be typical? What would be the shape of the histogram of that random variable x bar gotten by choosing a sample and computing its x bar? That's one case of a general question. If I have a numerical variable x with a mean mu sub x and a standard deviation sigma sub x, the subscripts are because I'm going to talk about the mean and standard deviation of other variables and I want to keep them straight. And then I consider all samples of size n. For each sample I compute x bar and I look at all those numbers and I ask I make a histogram of them. I ask what's the distribution, the sampling distribution of those sample means. Just like last lecture, there are 3 facts. I can tell you its mean, its standard deviation, and its shape. The mean of x bar, as we said before, is the same as the mean of x. We expect on average that sample mean to be the population mean. The standard deviation, remember we call that standard error when we're talking about a sampling distribution. The standard deviation of x bar is the standard deviation of x divided by the square root of the sample size. So it's going to be smaller than the standard deviation and get smaller the bigger n is. And then the third fact is it's roughly normal as long as n is big enough. Just like last time, those 3 facts are based on 3 assumptions. The first assumption, just as before, to do any of this, you have to assume that the sample is a simple random sample. So assumption A, SRS. The formula for the standard error is assuming you're sampling with replacement. That's generally not true, but it's good enough if your population is very large. So our second assumption, assumption B, is that the population is at least 20 times the sample size. Exactly the same large population assumption as before. The third assumption is wrapped up with a deep fact called the central limit theorem. The central limit theorem says if x is any distribution, as n gets larger, the sampling distribution of x bar for samples of size n approaches the normal distribution, looks more and more like a normal distribution. In general, when n is small, the distribution of x bar looks like the distribution of x. As it gets larger, it becomes more and more unimodal, and then it becomes more and more symmetric until it starts looking exactly like the normal distribution. We saw in class some examples of adding or averaging variables together tending to make things look normal. This is the precise version of that. So here's an example. If I started out with a very skewed, right-skewed, multimodal distribution, if I took averages of 4 things chosen from this population, I would get still a very right-skewed multimodal distribution. By the time I got up to n equals 8, still multimodal and right-skewed, but you can see the highs are lower and the lows are higher, and things are a little more scrunched together. By the time I get up to 16, it's still highly skewed, but the peaks and troughs start to look like wobbles around something that's almost unimodal. By the time n is 32, in this case, it's clearly unimodal, although quite skewed. By the time you get to, n equals 64, you can see that it is very slightly skewed, but looks very much like a normal distribution. By the time n is 128, it's almost indistinguishable from a normal distribution. The effect of the central limit theorem means you can count on x bar being roughly normal if x itself is pretty close to normal, or if n is very large, or if x is somewhat normal and n is somewhat large. So there's a graded scale of how good you need each of those to be, which we will summarize in the rather complicated 0-15-40 rule, which covers all your bases. Here's the 0-15-40 rule. It says that x bar can be taken to be normal if one of the following conditions is met. You only need one to be met. Either the population distribution x is known to be normal. If x is normal, you're all set. You don't need to know anything about n. Or, here's the intermediate case, if the sample size is at least 15 and x is not too skewed and doesn't have any huge outliers. In other words, if x is okay and n is pretty big. And finally, if n is more than 40, or 40 or more, you don't need to know anything about x. I'm going to illustrate that. We're going to do a few examples together, and you'll start to see how using the 0-15-40 rule works, in fact, how using all the assumptions works. So back to our first example. Young American men's heights, bell-shaped, mean of 70, standard deviation 2.5. You take a simple random sample of 12 young American men, and you compute their average height, x bar. I have a bunch of questions to ask. What's the mean and standard deviation of x bar? What's the chance that x bar will be more than 6 feet, less than 5 foot 6 inches? What's the chance it'll be between two values? And what are the two values between which we can be 95% sure the answer will fall? Just as in last lecture, this time through, I'm going to interweave the assumptions with the facts that follow from them, so you get a sense of where the logic is. But in the future, we will generally compute all the mean, the standard deviation, and probabilities separate from checking the assumptions. It's just a lot simpler to do it that way, even though this is more logical. First assumption, it says it's a simple random sample. That's usually how we will check it in practice. So we know, since the mean of x is 70, that means the mean of x bar is also 70. X bar is centered around 70. Second assumption, we need the population, which is all young American men, to be at least 20 times the size of the sample, which is 12. So we need there to be at least 240 young American men? No problem. There's way more than that. So we can compute the standard deviation, or standard error, which is sigma x 2.5 divided by the square root of 12, the sample size, and that works out to 0.722. Notice that's much smaller than the original standard deviation. X bar tends to have a much smaller spread than x. All right? The third assumption is the 0-15-40 rule. N is 12, so it's not more than 15 and it's not more than 40, which means no hope of meeting assumptions, versions 2 or 3 of the assumption. However, we were told that x is bell-shaped, so it meets condition 1. Bell-shaped, roughly normal, symmetric and unimodal. If it tells you anything that specific about the distribution, that's good enough to meet the 0-15-40 rule. Therefore, we can assume x bar is a normal distribution with a mean of 70 and a standard deviation of 0.722. Now we can go to town computing probabilities. The probability that x bar is more than 6 feet, or greater than 72 inches, because it's a normal distribution, we use norm dist. Because it's greater than a value, we take 1 minus norm dist 72, and then we enter the mean of 70 and the standard error of 0.722, and then we put in a 1. And the answer is very small, 0.279%. Again, this calculation is very sensitive to the standard deviation. You need to make sure to round to enough decimal places, or more simply, if you put the exact formula in, if you enter into that slot 2.5 slash SQRT open parentheses 12 close parentheses, then Excel will take it out as accurately as it can manage, which is always fine in my experience. What's the chance X bar will be less than 5 foot 6 inches or 66 inches? Less than 66 is equal to norm disk 66. Everything else is the same, and we get a teeny tiny probability. Then it asks, between what two values will 95% of the sample's sample means fall? Well, of course, the empirical rule tells you within 2 standard deviations, but we can do a little better than that. Since X bar is normal, we know that in fact it's within 1.96 standard deviations of the mean that 95% of the data falls. So the answer is 70 plus or minus 1.96 times the standard error, which works out to between 68.6 and 71.4 inches. So that's a pretty narrow range in which 95% of the time your sample mean will fall. Let's do another example. Haircuts of American college students cost on average $18 with a standard deviation of $22. What's the probability that a simple random sample of 52 college students will have an average haircut of less than $16? How about between $17 and $19? Between what two values would 95% of all such samples fall? And finally, if I actually got an average of 30 in my sample, would that suggest there was something wrong with my sampling or with my presumed mean or standard deviation? So, asking about the average of a sample of 52 is asking about X bar. It says it's a simple random sample, so we meet assumption 1. Therefore, mean of X bar is 18. There are more than 20 times 52, 20 times the sample size, college students. More than 1,000 college students in the world, so the large population assumption is met, so we can assume that sigma of X bar is 22, the sample standard population standard deviation, divided by the square root of 52, which is the sample size, or 3.05. That's the mean and standard error, the 0, 15, 40 rule. In this case, n is 52. It's more than 40, so assumption 3 is met, so you are done. As soon as you know 1 is met, you don't have to check the other two. I noticed here that the other two are not met because we don't know the shape, anything about the shape of x. In fact, it's actually pretty obvious from the mean and standard deviation that x is skewed right. But as soon as you meet one assumption, you've met the 0, 15, 40 rule. Now we can calculate probabilities with norm dist, because we know it's normal. Probability that X bar is less than 16, norm dist of 16. You put in the mean, you put in the standard error, you put in 1, and that works out to 25.6. The probability of being between 17 and 19 is norm dist of 19 minus norm dist of 17. All the other stuff is the same, and that is 25.7%. 95% of samples fall within 1.96 standard errors of the mean, 18 plus or minus 1.96 times 3.05. So 95% of the time, that sample will give you a sample mean between $12 and $24. Okay, and finally, that last weird question. I asked, would getting 30 be a surprising result? This is something that's going to come up a lot in the future. At what point is something so surprising that you have to question what you were presuming up to that point? So we've talked about how surprising something is by looking at its z-score, and that's a fine way to approach it. But another way to say it is, what's the chance of getting something as big as 30? What's surprising about 30 is how big it is. What's the chance of getting something that's at least as big as 30? 30 or higher, well, that's 1 minus norm dist of 30, with all the other things the same, and that works out to 4 times 10 to the negative fifth, so 4 chances out of 10,000. That is really unlikely. If something really unlikely happens, based on what you were presuming, then probably what you were presuming is wrong. So probably something about what you figured was true, the mean, or maybe the standard deviation, or that you took a simple random sample, or one of the other assumptions, is incorrect. Something is wrong with what you used to get that calculation. That logic we will come up against again and again. You will get used to it. Okay, now I want you, if you haven't been doing these on your own, I want you to try doing this on your own. So, college students' heights are bimodal and symmetric with a mean of 68 and a standard deviation of 3.5 inches. If you take a simple random sample of 18 college students and compute their average height, x bar, I want you to do two things. I want you to find the mean and standard error of x bar. I guess there's three things. Check all the assumptions, and find the probability you'll get an average height for your sample over 70 inches. Pause the tape, do these calculations, write them down, come back, and see how you did. All right, let's go through it. It says it's a simple random sample. That assumption is met. There are more than 20 times 18 college students, so the large population assumption is met. N is 18, that's more than 15, and we're told that x is symmetric. So version 2 of the 0, 15, 40 rule is met. So we can assume x bar is normal. That means the mean of x bar is 68. The standard error of x bar is 3.5 over the square root of 18, which is 0.825. So the probability that x bar is more than 70 is 1 minus norm dist of 70, 68, 3.5 divided by square root of 18, all, 1, close parentheses, and that works out to just under 1%, 0.767%. Okay, if you're like most people, the 0, 15, 40 rule with its multiple conditions, each of which is a little tricky, is confusing, and in particular is hard to remember. You will get used to using it, but here's a mnemonic that will help you remember it. You just have to be willing to do one thing, which is take my advice on how to be cool. Oh, what's my advice going to be? Well, it's going to depend on how old you are. Okay? So if you're under 15, if you're a kid, you remember when you were a kid, to be cool, what you needed to be, you needed people to think you were normal. You needed to be known to be normal. And sure enough, our first version of the assumption is that x is known to be normal. For those of you who are between 15 and 40, there's lots you can say about your achievements and your worth and your kindness, but the truth is, of course, you have to look good. And sure enough, if n is greater than or equal to 15, the histogram has to look good. It has to be not too skewed, no major outliers. And finally, and most importantly, if you're over 40, you don't have to do anything, you just are cool. This is a mnemonic I thought up on my 40th birthday. So, here's what you should know having watched this lecture. You should be able to say what we mean by the sampling distribution of x bar and what it represents. That is, all the possible values of x bar as you run through all possible samples. You should be able to calculate the mean and standard deviation of x bar. You should be able to check all three assumptions: the simple random sample assumption, the independence large population assumption, which tells you that the standard deviation formula is correct, and the normality or 0, 15, 40 rule, which tells you that you can use norm dist. And you should be able to calculate the probabilities of x bar falling in various ranges using norm dist. This ends the lecture. I have a little bonus slide to help you navigate something that people find confusing. What we just did, we're going to do over and over again, which is explain how to do something in the categorical realm when you're dealing with a categorical yes or no question, and then explain how to do it in the numerical realm. They are just similar enough that it's easy to mix them up, but just different enough that it's really important to keep them straight. So if right now you build a wall in your brain between the categorical world and the numerical world, and just see the similarities as analogies, your life will be easier. So just to summarize, if your population distribution is categorical, if it's a yes or no question, then you have the parameter of interest is p, the population proportion. The statistic is p hat, the sample proportion. The mean of p hat is p. The standard deviation of p hat is given by that complicated formula. And p hat is normal. Our assumptions are simple random sample, the large population assumption, that the population is at least 20 times the sample size, and the rule of 15, that n times p and n times 1 minus p are at least 15. On the other hand, if your population distribution is numerical, if you start with a variable, a question whose answer is a number, and it has a mean mu and a standard deviation of sigma, the parameter is the population mean, the statistic of interest is the sample mean x bar. We know that mu of x bar is mu of x. We know sigma x bar is sigma x over the square root of n. We know that x bar is normal. And our assumptions, first two are exactly the same. Simple random sample, large population. But in the numerical world, the third assumption is the 0, 15, 40